Hello again, Physics 243. In this optional video, I want to go over the derivation of the Doppler formula. Where does it come from? I just want to give you a sense of how it's calculated. Okay, Doppler effect. So here's a source, and here I'm showing wave fronts. So this one was emitted first, and then after some time, this one gets emitted, and then that, they propagate outwards. So wavefront, think of that as the region where the pressure in the air is highest or where the molecules are most compressed. Okay, and then the wavelength is the distance from one wavefront to the other. And again, they radiate outwards. Right, let's say that this source emits wavefronts at a frequency f. That means that the time between the emissions is, well, that's the period, so that's 1 over the frequency. Okay, remember that the speed of sound equals wavelength times frequency. And since the period is 1 over the frequency, I can invert that and replace the frequency with 1 over the period. So the speed of sound could be written either as wavelength times frequency or wavelength divided by period. Okay, so if I take this last one equals v sound, I can write the period this way. So the period is the wavelength divided by the speed of sound. I'm going to use this one, so I'll put a box around it. Okay, now suppose that the source moves towards the right with a speed v source. So this orange dot is going to move to the right with a certain speed. And in time t, t meaning the period, it moves a distance, d source equals v source times the period. So that's this distance here. And what the effect is that it shortens the distance between the emitted wavefronts, right? Because it emits one, and as that one starts to move out, the source moves to the right before it emits another one. So we have that the new wavelength, lambda prime, is the old wavelength minus this distance right here. And that distance is how far the source went in one period. Okay? So here I just plug this equation in there. And now remember that I had this on the previous slide. Period is wavelength divided by v sound. Plug that in for the period. I have this. Now I can factor a lambda out to make it a little more elegant. There we go. Okay, so this gives me the new wavelength in terms of the two speeds, speed of the source and speed of sound. This is the wavelength that would be measured by a stationary observer who receives these wavefronts. So there's an observer, and that observer would perceive a frequency given by, well, there's this relationship as well. So the speed of sound is this new wavelength times the new frequency. Okay, so solving that for the new frequency, because that's what I want to figure out, I have v sound divided by lambda prime, and the lambda prime is up here at the top. Plug that in there like that. So v sound, this is the v sound, and then lambda prime is this whole denominator. Come from up there. Now have a look at this, v sound divided by lambda. Well, that's the same as this, except for the prime. So if I remove the prime from the other side, I have the frequency without the prime equals v sound over lambda without the prime, which is what I have here. So that's just this f. This fraction right here, v sound over lambda, is this f. Okay, so this is good. Now we have an expression for the frequency that the observer measures in terms of the original frequency and the speed of the source and the speed of sound. Okay, so that's valid when the source moves towards the observer. Now, to make it look a little nicer, I'm going to multiply it by v sound divided by v sound and then distribute this in the denominator. And I get this. It just kind of looks a little bit nicer, and it's closer to my end result. By the way, notice that this new frequency that's observed by the observer is bigger than the original frequency because I'm subtracting something from V sound in the denominator. So I have to make the denominator smaller, which then makes F prime bigger. Right? Now, if we do the same analysis with the source moving away, everything follows through except that there's a minus sign that has to be taken into account, which ultimately results in this being a plus sign. So I invite you to go back and follow that. It's the same argument except that the source is going the other way, and you'll get this. In this case, notice that the observed frequency is less than the emitted frequency. The source moves away, and the observer measures the lower frequency. That's because this denominator is larger than the numerator. Right? Well, is larger than, in this case, larger than the numerator. So we can combine both of those results. I've written them in the same form. The only difference is the sign there. So that formulation there works with these two rules then. If the source moves towards the observer, use the upper sign. If the source moves away from the observer, use the lower sign. Okay. All right, so this is the result for a moving source. What if the source is stationary, but the observer moves? So we have a little bit different argument for that case. Here's the picture. Source is stationary, emitting wave fronts with wavelength lambda. Speed of sound is the speed at which the wave fronts propagate. And now we have the observer moving. Let's say that it's moving towards the source with speed v observer. Right, so the observer, I'm assuming first that the observer moves towards the source. From the observer's perspective, the sound waves move at speed v sound plus v observer. Right? If he's standing still, he would see the wave fronts go at v sound, but he's moving at v observer towards them. So that makes it look to him that the wave fronts are going faster than they are when he was stationary. So we add these two speeds for that speed. So the observer detects a frequency. Remember these relationships? The observer detects a frequency f prime, which is this speed, the perceived speed of motion of the wavefronts, divided by the wavelength that's there. So plug this in there. And for lambda, I'm going to plug in this equation down here, right? V sound divided by f. And then I can just, f in the denominator of the denominator is in the numerator. And so this becomes this. Okay. So this is my result for when the observer moves towards the source. And once again, you can carry out the same argument with the observer moving away from the source. You just have a minus sign that you carry around, and it ends up with a minus sign here. Same argument, just with the observer going the other way. So combine all of those things together, and we get this formulation of the Doppler effect equation, with the rules that you use the upper signs if the source moves closer together, if the source and observer move closer together, and the lower signs if the source and observer move apart. Okay? That's it. So I hope you enjoyed that. And that's also it for the sound chapter. All right. Have a good weekend.